Hello everyone, I'm Professor Diwa, and welcome to a math video on logarithmic functions. Our objectives are to write exponential equations with logarithmic notation and write logarithmic equations with exponential notation. Solve logarithmic equations by using exponential notation. Identify and graph logarithmic functions. Alright, so let's get started. First, we have the logarithmic definition. It states here, if b greater than 0 and b not equal to 1, then y equals log base b of x, means x equals b to the y power for every x greater than 0 and every real number y. Notice here that they're defining the logarithm log base b of x as y, and y is actually the exponent on the base b. So a logarithm is actually the value of the exponent on the base b. We typically use this definition to convert an equation with logarithmic notation into exponential notation and vice versa. In the next examples, I'll show you how we apply this logarithmic definition. For example number 1, write as an exponential equation. For part A, we have log base 2 of 32 equals 5. To rewrite this as an exponential equation, we start with the base of the logarithm b, which is the value of 2. This means that the value of the base of the exponent is 2. Next, we move on to the value of the exponent y. The logarithm is equal to the value of the exponent, which is 5. So we get 2 to the 5th power. Next, we set this equal to the value of x, which is the number in front of the logarithm, 32. So we have 2 to the 5th power equals 32. You could see here that this is true. 2 to the 5th power is 32, so everything is correct. Moving on to part B, we have log base 2 of the square root of 2 equals 1 over 2. First, we start by writing out the base of the exponent, which is the same value as the base of the logarithm, which is 2. Next, we write in the value of the exponent. The logarithm is equal to the value of the exponent, which is 1/2. So we get 2 to the 1/2 power. Next, we set this equal to the value in front of the logarithm, which is the square root of 2. So we have 2 to the 1/2 power equals the square root of 2. This is true, so everything is correct. Next, we move on to part C. We have log base 2 of 1 over 8 equals -3. Again, we start with the base of the exponent, which is the same as the base of the logarithm, so we get the value of 2. Next, we need to write in the value of the exponent. The logarithm is equal to the value of the exponent, so we have -3 for the exponent. Now we have 2 to the -3 power. We set this equal to the value in front of the logarithm, 1 over 8. We get 2 to the -3 power equals 1 over 8. This is true, so everything is correct. Next, we have a practice problem. Write as an exponential equation. For part A, we have log base 3 of 81 equals 4. For part B, we have log base 7 of 7 equals 1. For part C, we have log base 10 of 0.1 equals -1. Alright, so go ahead and pause the video, work out each problem, and then check back with the video to see the solutions. Alright, so let's go over part A. First, we start off with the base of the exponent, which is 3. The logarithm is equal to the value of the exponent, which is 4. And then we set this equal to the value in front of the logarithm, 81. So we get 3 to the 4th power equals 81. For part B, we start off with the base of the exponent, which is 7. The logarithm is equal to the value of the exponent, which is 1. And then we set this equal to the number in front of the logarithm, which is 7. So we get 7 to the 1 power equals 7. For part C, we start off with the base of the exponent, which is 10. The logarithm is equal to the value of the exponent, which is -1. And then we set this equal to the value in front of the logarithm, 0.1. We get 10 to the -1 power equals 0.1. In example number 2, write each as a logarithmic equation. For part A, we have 9 cubed equals 729. To rewrite this as a logarithmic equation, we're going to use the logarithmic definition. First, we start off with the base of the logarithm b, which is the same value as the base of the exponent, which is 9. Next, we need to find the value for x, which goes in front of the logarithm. The value for x is the same value that 9 cubed is equal to. This is 729. Finally, we need to find the value for y. The value for y is the same value as the exponent, which is 3. So we have log base 9 of 729 equals 3. Next we have part b. We have 6 to the negative 2 power equals 1 over 36. First we start off with the base of the logarithm, which is the same value as the base of the exponent, which is 6. Next we write in the number that goes in front of the logarithm. This is going to be the same value that 6 to the negative 2 power is equal to, which is 1 over 36. The last step is writing in what the logarithm is equal to. The logarithm is equal to the value of the exponent, which is negative 2. So we get log base 6 of 1 over 36 equals negative 2. Moving on to part C, we have 5 to the 1/3 power equals the cube root of 5. First we start off with the base of the logarithm, which is just going to be 5. Next we write the value in front of the logarithm, which is the cube root of 5. Next, the value of the logarithm is equal to the value of the exponent, so we get 1 over 3. The final answer is log base 5 of the cube root of 5 equals 1 over 3. For part D, we have pi to the 4th power equals x. We start with the base of the logarithm, which is pi. The value in front of the logarithm is going to be x, and the logarithm is equal to the value of the exponent 4. So we have log base pi of x equals 4. Next, we have a practice problem. Write each as a logarithmic equation. For part A, we have 4 to the 3rd power equals 64. For part B, we have 6 to the 1/3 power equals the cube root of 6. For part C, we have 5 to the negative 3rd power equals 1 over 125. For part D, we have e to the 7th power equals z. Alright, so go ahead and pause the video, try out this problem, and then check back with the video to see the solutions. Alright, so let's go over the solutions. For part A, we start off with the base of the logarithm, which is 4. The value in front of the logarithm is 64, and the logarithm is always equal to the exponent, which is 3. So we have log base 4 of 64 equals 3. For part B, we start off with the base of the logarithm, which is 6. The value in front of the logarithm is the cube root of 6, and the logarithm is always equal to the exponent, which is 1 over 3. So we have log base 6 of the cube root of 6 equals 1 over 3. For part C, the base of the logarithm is 5. The value in front of the logarithm is 1 over 125, and the logarithm is always equal to the exponent, which is negative 3. So we have log base 5 of 1 over 125 equals negative 3. For part D, the base of the logarithm is e, the value in front of the logarithm is z, and then the logarithm is equal to the exponent 7. So we have log base e of z equals 7. For example number 3, solve. For part A, we have log base 5 of 1 over 25 equals x. We need to solve this logarithmic equation for x. The first thing we need to do is rewrite this as an exponential equation. We start off with the base of the exponent, which is 5. The exponent is going to be x, and then we set this equal to 1 over 25. From here, we need to rewrite 25 as an exponent with the base of 5. This would be 5 squared. So we have 5x equals 1 over 5 squared. Next, we need to rewrite this so it's no longer a fraction. We could do this by converting the exponent into a negative exponent. This would be 5 to the negative 2 power. So we have 5x equals 5 to the negative 2 power. Now that the bases of the exponents are the same, we can apply the uniqueness property of exponents. We get x equals negative 2, And our final answer in set notation is curly bracket -2, close curly bracket. Moving on to part B, we have log base x of 16 equals 2. Again, we start by rewriting this as an exponential equation. The base of the exponent is x, the exponent will be 2, and we set this equal to 16. We get x squared equals 16. Next, we need to solve for x by getting rid of the square. We just take the square root of both sides of the equation. After simplifying, we get x is equal to -4 and +4. However, we only have one solution because the base of a logarithm must be a positive value and it cannot be equal to 1. So for our final answer in set notation, we have a set of curly brackets and 4 on the inside. Moving on to part C, we have log base 26 of x equals 2. Rewriting this as an exponential equation, we have 26 squared equals x. The next step here is just squaring the 26. We get x equals 676. Our final answer in set notation is curly bracket 676, close curly bracket. Next, we have a practice problem, solve. For part A, we have log base 4 of 1/4 equals x. For part B, we have log base x of 9 equals 1/2. For part C, we have log base b of 1 equals x. For part D, we have log base 10 of 1000 equals x. For part E, we have log base 8 of x equals 2/3. And for part F, we have log base 2 of 32 equals x. Alright, so go ahead and pause the video, take your time working out these problems, and then check back with the video to see the solutions. Alright, so let's go over the solutions. For part A, we first convert this into an exponential equation. We get 4 to the x power equals 1/4. Next, we use negative exponents to get rid of the fraction. We get 4 to the x power equals 4 to the -1 power. Next, we use the uniqueness property of exponents. We get x equals -1. Our final answer in set notation is curly bracket -1, close curly bracket. For part B, we start by rewriting this as an exponential equation. We get x to the 1/2 power equals 9. Next, we could convert the exponent of 1/2 into a radical. This would be the square root of x equals 9. Next, we get rid of the radical by taking the square of both sides of the equation. After simplifying, we get x equals 81. So the final answer in set notation is curly bracket 81, close curly bracket. For part C, we rewrite this as an exponential equation. We get b to the x power equals 1. The only possible value that we can get for x so that b to the x power is equal to 1 would be 0. So we have x equals 0, and our final answer in set notation is curly bracket 0, close curly bracket. For part D, we rewrite this as 10 to the x power equals 1000. Next, we rewrite 1000 as 10 cubed, so we have 10 to the x power equals 10 cubed. From here, we apply the uniqueness property of exponents. We get x equals 3, and our final answer in set notation, we have a set of curly brackets and 3 on the inside. For part E, we rewrite this as 8 to the 2/3 power equals x. Next, we could convert 8 to the 2/3 power into radical notation. We would have parentheses, the cube root of 8, and a square on the parentheses, equals x. Next, we take the cube root of 8, which is 2, so we have 2 squared equals x. The square of 2 is 4, so the result is x equals 4. The final answer in set notation, we have curly bracket 4 and then a close curly bracket. Moving on to part F, we rewrite this as 2 to the x power equals 32. Next, we rewrite 32 as 2 to the 5th power. We get 2 to the x power equals 2 to the 5th power. From here, we apply the uniqueness property of exponents. We get x equals 5, and our final answer in set notation is curly bracket 5 and a close curly bracket. Next, we're going to go over 3 properties of logarithms. It states here if b is greater than 0 and b not equal to 1, then 1, log base b of 1 equals 0. 2, log base b of b to the x power equals x. 3, b to the log base b of x power equals x. In the next example, we're going to use these three properties to simplify logarithms. For example number 4, simplify. For part A, we have log base 3 of 3 squared. To simplify this logarithm, we just apply property number 2. This logarithm would simplify to the value of the exponent, which is 2. Another way we could work this out is setting this logarithm equal to some value x. From here, we could solve this by converting it into an exponential equation. This would be 3 to the x power equals 3 squared. Using the uniqueness property of exponents, this becomes x equals 2. Moving on to part B, we have log base 7 of 7 to the negative 1 power. Again, we just apply property number 2 to simplify this. We get that this simplifies to the value of the exponent, which is negative 1. Moving on to part C, we have 5 raised to the log base 5 of 3 power. To simplify this logarithm, we apply property number 3. This logarithm simplifies to the value in front of the logarithm, which is just 3. Next, we have a practice problem, simplify. For part A, we have log base 6 of 6 cubed. For part B, we have log base 11 of 11 to the negative 4 power. For part C, we have 3 raised to the log base 3 of 10 power. Alright, so go ahead and pause the video, try out this problem, and check back with the video to see the solutions. Okay, so let's go over part A. For part A, we apply property number 2, so this logarithm simplifies to 3. You can also work this out by setting the logarithm equal to x. We have log base 6 of 6 cubed equals x. Converting this into an exponential equation, we get 6 to the x power equals 6 cubed. Next, we apply the uniqueness property of exponents. We get x is equal to 3. For part B, again, we apply property number 2, so this becomes negative 4. For part C, we apply property number 3, so this simplifies to the value of 10. Next, we have the definition for a logarithmic function. It states here, if x is a positive real number, b is a constant positive real number, and b is not 1, then a logarithmic function is a function that can be defined by f of x equals log base b of x. The domain of f is the set of positive real numbers, and the range of f is the set of real numbers. In the next example, we're going to go over the graph of a logarithmic function. For example number 5, graph the logarithmic functions. For part A, we have y equals log base 2 of x. To graph this function, we're going to use the point plotting method. Below I have an x and y table. For the x values, I'm going to use 0.5, 1, 2, 4, and 8. To find the corresponding y values, you can just use a graphing calculator or a regular scientific calculator. Now, if you're not able to input the base of 2 into your calculator, you could use this formula here to find the y values. You could use y equals log of x over log of 2. Substituting the value of 0.5 in for x, we get negative 1 for y. For x equals 1, we get the value of 0 for y. For 2, we get 1. For 4, we get 2. And for 8, we get 3. Next, we go ahead and plot these points on a graph. We have 0.5 comma negative 1 over here, 1 comma 0 over here, 2 comma 1 over here, 4 comma 2 over here, and finally we have 8 comma 3 over here. Next we draw a curve through our points, and now we have the graph of y equals log base 2 of x in blue. Moving on to part B, we have y equals log base 1/3 of x. Again, we're going to plot this using the point plotting method. Below we have our x and y table. For the x values, I'm going to use 1/3, 1, 3, and 9. To find the y values, we're going to use a calculator. If you're not able to input the base of 1/3 in your calculator, you could use the formula y equals log of x over log of 1/3 to find the value of y. When we plug in 1/3 in for x, we get 1. For 1, we get 0. For 3, we get -1. And for 9, we get -2. Next, we go ahead and plot each point. 1/3, 1 is here. 1, 0 is here. 3, -1 is here. And 9, -2 is here. Now we go ahead and draw a curve through our points. So here's the graph of y equals log base 1/3 of x in red. Next, I want to point out a few things about our graphs. Notice here that both graphs have an x-intercept at 1, 0. Also, both graphs do not have a y-intercept. The graphs get really close to the y-axis, however they never touch. There's actually what we call a vertical asymptote right on top of the y-axis. It's not part of the graph, it's just a guide to help graph the logarithmic function. The domain for both graphs are all x values greater than 0. The range for both graphs are all real numbers. Both of the graphs pass the horizontal line test, meaning that they are one-to-one functions. The last thing I want to point out is the shape of each graph. For the graph of y equals log base 2 of x, the graph starts off low, and as the x values start increasing, the graph increases towards the right. This happens whenever the value of the base b is greater than 1. You can see that the value of the base here is 2. If we take a look at the graph of y equals log base 1/3 of x, our graph starts off really high, and as the x values start increasing, the graph starts decreasing towards the right. This happens whenever the value of the base of the logarithm is between 0 and 1. You can see that the value of the base here is 1/3. The last thing we have is a table that summarizes the characteristics of logarithmic functions. For the function f of x equals log base b of x, where b is greater than 0 and b not equal to 1, we have that this logarithmic function is a one-to-one function. The x-intercept would be at the point 1, 0. There are no y-intercepts. The domain would be parenthesis 0, infinity, close parenthesis. The range would be parenthesis -infinity, infinity, close parenthesis. Now we have two graphs below. Starting with the graph on the left, this is the graph of f of x equals log base b of x if b is greater than 1. You can see here that the graph starts off really low, and as the x values increase, the graph increases towards the right. We have an x-intercept at 1, 0, and we also have a point at b, 1. For the second graph on the left, this is the graph of f of x equals log base b of x if b is a value greater than 0 and less than 1. We can see here that the graph starts off high, and as the x values increase, the graph starts decreasing towards the right. We have an x-intercept at 1, 0 and a point at b, 1. Alright, well this wraps up our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.